Okay, so I'm gonna start the recording. Does anyone else want to say something on that? Maybe. If not, I'm just gonna go ahead and share my screen. Oh, that is not the screen I wanted to share. Can everybody see my PowerPoint?
Yes.
Great. Okay. Solid. Love that. Okay. So today we're talking about muscles and contraction. So everybody knows that in your body, two of the main components that help you move are your skeletal system, so your bones. Your skeletal system is very important to supporting your body. And then you have muscles. And muscles are the things that allow you to move your bones, that allow your heart to beat, and allow your intestines to digest certain foods. And it even allows your stomach to pump. So it can mix the food in your stomach. And so today we're going to talk about muscles. But before I get into the kind of really biological.
I know these muscles.
What's up?
I know these muscles.
Okay, great. Solid. Yes, this is the very basic of muscles, but we'll also talk about myosin and actin and myofibrils, and so we'll get into the details. So don't worry, Daniel. But just by a show of hands, or maybe send me a little message in the chat. How many of you guys play sports? Okay, yes. The chats are pouring in, and Anthony has raised his hand. So yes, it does seem like okay. Ping pong. VME. I'm not sure what VME is, John.
Oh, that's a typo.
It's what? Oh, a typo. Sorry. Okay, yeah, typo. But yes, it does seem like most of you guys do play sports. So usually after you play sports or you run, you'll feel kind of sore, right? Have you guys felt that feeling where your muscles are kind of tired and they might even hurt a little bit when you go to move them? That's because you're actually, number one, you're building up lactic acid in your muscles and you're creating micro tears. So that's how you build more muscle. When you go to work out muscles, you actually end up tearing the muscle a little bit, and they're called micro tears. And so when you create these micro tears, your body is like, oh no, these micro tears are bad, obviously. And your body goes to repair these micro tears. And when it does repair the micro tears, it makes the muscles stronger so they don't tear as easily. And that is how you build muscle. That's why you see bodybuilders with huge muscles and other sorts of athletes with very large muscle groups per se. Micro tears are good. They make your muscles stonk. Yes. Stonk. Nice. I can see you guys are still young, but yes, they do make your muscles stronger. Okay, let's talk about the biology side of muscles now. So generally we recognize three main muscle types. The first being cardiac. Does anyone know what the word cardiac refers to?
Yeah, sort of. Like, so like it's like when it's like I've heard it before.
I'm not sure what you're saying, Daniel, but it's also okay if you don't know. Yes, Lena.
I have a question.
Oh, yes, go ahead.
Basically, the muscle tears will make you buff. In other words.
Yes. The muscle tears will eventually make you buff, but you have to tear them over and over and over again. You have to consistently work out. You can't just expect
So
to
that
lift one weight.
That means when you work out, when you get muscle tears, that means when you get more muscle tears, they'll get harder to like tear. And
Exactly.
then the more harder it gets to tear, the more harder you can get to buff.
Yes, that is also true. Very good comment, Daniel.
That makes games really, really unrealistic. Not realistic.
Yes. When you start building up a lot of muscle, it gets harder and harder to build more muscle. Eventually, your muscle growth will sort of plateau, and that's where we get into
Wait,
like
can your
protein
muscles
powder and stuff.
can your muscles stop growing?
Um, I would not say that you could ever reach a point where your muscles would stop growing, but you could reach a point where it is very difficult to grow more muscle because you have so much already on your body and because your muscles are so strong and you have to put many hours into working out these muscles. That's what
Will your,
bodybuilders do, though. That's
will
their job.
your muscles get so heavy that like your legs muscles can't like hold your upper muscles?
Mm,
Probably not.
I probably don't think so. The human body is pretty good at regulating itself. And if you're getting so heavy on top that your legs are going to collapse, then your body is going to tell you, okay, you need to work out your legs or we're going to start cutting muscle from the top of your body. So your body is pretty smart about that. I wouldn't worry about that. Okay, but yes, let's get back to the three main muscle types. The first one being cardiac. These cardiac cells are in your heart. And they are something that we call involuntary, which means that you cannot control how these muscles beat, how they contract. And that makes sense, right? When we think about our heart, we don't really control the way our heart beats. The heart beats by itself. It has an electrical pacemaker, and it basically sends out electrical signals, and the heart goes lub dub, lub dub, lub dub. And we basically can't control it. And so those are cardiac cells. The second kind is something we call smooth muscle cells. And it's this last column over here. And so smooth muscles can often be found in organs. So let's say the liver, which helps detoxify the bloodstream, the pancreas, or the intestines, which help digest food, both the small and the large intestine. And smooth muscles are also involuntary. We cannot control them. That is because, well, if you think about it, does anyone here know how to control their own liver? I would assume not. I mean, that
You
would be
just
pretty crazy.
you just don't like you just don't pee, you know?
You just don't pee. Okay, so on that, usually it is the kidneys and the bladder that deal a lot with urine. The kidneys usually work to filter urine in certain circumstances, and the bladder is what stores the urine in your body. But I'm sure the bladder is also made of smooth muscle cells. And if you think about it, actually, the bladder might be made of skeletal. I'm not sure. I'm gonna have to look at that. But generally organs are made of smooth muscle other than the heart or that kind of thing. So your stomach, it's made of smooth muscle, and you can't really control the way your stomach contracts. Oh, there's a question in the chat, maybe. Oh, someone said bruh. What's up, Lena?
Right.
Lena, did you have a question? Okay.
Never mind.
Okay, never mind. Feel free to ask, by the way, Lena. There are no dumb questions. Okay, but our last muscle type is skeletal. And skeletal is what we can control. So when I go to talk, those are skeletal muscles that are moving my jaw. When I go to lift my arm, it is my bicep and my tricep going to lift my arm. When I go to run, my butt muscle is helping support my running. My quadriceps are or my quads, or basically my thighs, they are helping to support my running, as well as my calves. So any type of muscle that is voluntary and connected to bones can be thought of as skeletal. These are the muscles that help us run, jump, play, any kind of physical activity. If you guys swim, you guys are using your skeletal muscles. If you guys play tennis, if you guys are playing soccer, basketball, you are using your skeletal muscles. Any questions, anybody?
Are skeletal muscles based off of based off the
Daniel, you're cutting out a little bit. Are they based off of what?
skeletons.
Yes, the skeletal muscles are typically attached to the skeleton.
No, is like the name skeletal from
Yes,
the
yes. The name skeletal is based off skeleton because these muscles are attached to the skeleton. Is that okay, Daniel?
Yeah.
Okay, great. Solid. If there are no questions here, we're going to move to muscle structure. And this is where it gets a little bit more convoluted. So let's talk about the structure of muscles. So muscles are made of myofibrils, which are basically muscle fibers in a cell. If you guys have seen extreme bodybuilding or something, their muscles look like they have fibers in them, and those are the individual myofibrils, which is pretty cool to see, to be honest. But I wouldn't say worrying, but it's okay. Point is, it's very impressive. And so myofibrils are, as I said, muscle fibers in a cell. And myofibrils are made of something that we call sarcomeres. Sarcomeres are basically shortened lengths of myofibrils. They're kind of the unit for a muscle. So if we come in and we zoom in to, let's start with this picture. Each one of these little column guys, let me go grab my annotation pen. Here we go, annotation pen. Each one of these little column guys that I've just circled here, each one of these is a myofibril. However, in each one of these myofibrils, we have something called sarcomeres. And each one of these little circles I'm drawing now is a sarcomere. And so sarcomeres are kind of the basic building block of muscles, same way, let's say atoms are the building blocks of matter. And so let me clear all this. And now that we know that
Hey, I have a
sarcomeres,
question.
yes, what's up?
In the other other
Slide.
animation and the other animate no that slide in the anim that picture with the word thing, what are those red things, the red beam thing about?
Oh, okay. You're talking about this little guy, right?
Yeah.
This is actually the nucleus of the cell.
Oh, but
Yeah.
there's two.
Believe it or not, some cells can have two nuclei. Because muscle cells can be super long, they can actually have two nuclei, believe it or not.
Oh.
Yes. Yes. And because muscle cells also are constantly working, they're constantly in in progress is not the right word, but they're constantly in a state of activity. They typically do need more materials and more command centers, such as nuclei. Okay, but let's take a look at the individual sarcomeres. Inside a sarcomere, we have something we call actin and something we call myosin. And so actin and myosin are something we call filaments. And basically, they can slide next to each other. Kind of like if you guys have ever seen like teeth lock. If you have actin and you have myosin, they can slide together and they can kind of they are not they won't lock together, but they can slide past each other. It's like trying to think of a really good analogy here. It's like how your teeth can somewhat slide next to each other, or gears. Gears can mesh. Does everyone know that word, mesh? Okay. I don't think many people know that word, unfortunately. But basically when the teeth of a gear connect with the teeth of another gear, we call that mesh. And the same thing can happen with the actin and the myosin filaments, and they will mesh together and they can actually slide past each other. And we'll talk about this sliding and why the sliding is important. But just remember that actin is the thin filaments pictured in blue here, and myosin are the thick filaments pictured in orange here. And so just remember actin being thin, and myosin is thick. There appears to be something in the chat here. Isn't mesh breaking down? Not always. Mesh usually implies combining, John, or in some way working together. Yeah, that's what mesh implies. Mesh is also the thing on your windows that leaves that prevents the bugs from getting in. We call that window mesh. Yes. Okay. And now we are going to talk about muscle pull. Actually, let me talk about this little picture right here quickly. On the myosin, the thick orange filament, there are actually something called myosin heads. And we'll talk about why these things are important. And usually there are a bunch of myosin heads on a myosin filament. So this is only a picture of one of them, but just know that there are a bunch on this filament of myosin. Right. And this blue thing is the actin that's parallel to the myosin. Parallel means that they are on the same line, but they'll never touch. Okay. Oh goodness, this picture's so zoomed in. Okay, great. So the myosin head that I talked about earlier will actually accept ATP. ATP being the fancy word for it is adenosine triphosphate, but ATP is the energy of your body. It is the currency. And everything in your body that moves, that needs to perform any activity requires this ATP. And so when we go to contract our muscles, when we want to move our limbs, or we want to start running, or we want to jump, we need ATP. And this ATP actually binds to the myosin head. And this binding is pretty cool, but nothing really happens unless the ATP is broken down. And so let's talk about the breakdown. In this picture, we can see that the ATP has bound onto the myosin head. So we're one step closer to the muscle contracting. And the order of pictures I have messed up here. But we're starting here with the ATP binding to the myosin head. And then if we look at this photo on the very left right here, let me get my little annotation. When we're looking at this photo that I've just marked in an arrow, we're looking at the ATP being hydrolyzed. Basically, it is broken down into something we call ADP and a phosphate group. And in reality, we should talk a little bit more about ATP, but I will do that in another lesson. But now that the ATP has been broken down, the myosin head actually binds to the actin filament, the blue filament above the myosin head. And everyone can see that it kind of clicks on there, right? Is everyone good with that?
What clicks on where?
Okay, so the myosin head with the ADP on it can actually bind to the actin filament. It kind of just like clicks on there. I mean, it even says click right here. Is that okay?
So the ADP and the P click bind.
Yes. So the myosin head with the ADP and the phosphate attached can bind to the actin filament. Is that okay?
Yeah.
Okay, great. And so once this binding occurs, this myosin head is basically given energy. It has this ADP and the phosphate group on it, and we can think of the ADP and the phosphate as energy, basically. And so the myosin head now has all this energy, and it is bound to the actin filament. And I love this photo. I think it's a great representation. Basically, the myosin head, it contracts and it pulls the actin filament. Quite literally in the photo, it yells pull, and it pulls the actin filament along this kind of parallel line. And so that is how the muscle contracts. The filaments, when actin and myosin are pulled, they slide next to each other.
Wait, I have a question.
Yes, what's up, Daniel?
Where is all of this done.
Where is all of this done?
Mhm.
Okay, so this is in your muscle. When you go to lift a heavy object or flex your bicep or do a curl or something, your muscles are contracting, right?
Yeah.
Okay, so they contract basically to help you lift heavy objects.
Oh
And
wait, I just noticed my camera's outside.
oh, you're fine, you're fine. Um,
Oh,
But yes, what happens is the muscle has to contract, and for the muscle to contract, the two filaments slide next to each other. And we call this sliding filament theory. It describes how muscles can contract. Is that okay, Daniel? And these are happening in your skeletal muscles, as in like your bicep, your tricep, your quadriceps, your calves, whatever.
yeah.
Okay, great, solid. Glad to hear it. Okay, so basically, the pulling of the blue actin by the orange myosin head causes the two filaments to slide past each other. And because these two filaments are sliding past each other in the sarcomere, it compresses. And as the sarcomere compresses, let me go back to the previous slide. As these individual sarcomeres compress, the myofibril compresses and it pulls your muscle and it pulls your skeleton with the muscle. And so that is how muscles contract. Okay, guys, any questions? I'm happy to answer questions. This is a difficult topic. ATP, ADP, phosphate groups, and hydrolyzation is not something that is easily
Hey,
accepted.
I have a question.
Yes, great. What's up, Daniel?
The third picture on here
Yep.
is the first one. The first picture on here is the second one, and the second picture on here is the third one.
Yes. I'm actually going to label these for your viewing ease. My apologies. These are supposed to be in order, but this is 1, this is 2, and this is step 3.
So, wait. So, does the myosin head like pull the actin vertically or like horizontally?
It pulls it horizontally. The filaments, when the muscle head pulls, the filaments do not get closer. The myosin head is not like smushing the filaments together. Instead, the myosin head is pulling the filaments so that they're moving like this past each other.
Oh,
Yeah, they're not doing this. They're doing this.
oh.
That's why it's called sliding filament theory. The filaments
So then
slide.
it gets compressed, and then the cells get compressed, and then when it gets compressed, it moves the skeleton or like the muscle.
Exactly. When the filaments slide next to each other, the sarcomeres compress and the muscle contracts.
Mm.
That is also why you are able to lift heavy weights. These myosin heads are really pulling on the actin, and therefore your sarcomeres are really compressing to help you to help you lift that heavy weight.
I have another question that might not make sense.
Yes, what's up?
Don't you have to? Doesn't the myosin head have to have? Doesn't the myosin head have to have muscles to pull?
Okay. An interesting observation, Daniel. Myosin heads are significantly smaller than muscles. Myosin heads don't really have muscles themselves. It is myosin heads that makes up muscles.
Oh,
Yes. Remember that there are hundreds of thousands of myosin heads on a myosin filament. And so they each might be only pulling a little bit. But when you have so many and they all kick in and they all contract at the same time, you can actually get a really big curl. You can get a really big pull, and you can actually demonstrate a lot of strength. And your body is pretty good at this. We've gone through thousands of years of evolution, really.
Oh,
Yes. Okay.
wait. So
what's
that
up?
means that doesn't that mean that like during cavemen or like in the Bible, how if they had evolution, how do they like how do they move?
How do they make what?
How do because you said they had to the muscles evolved from time to time. So then the humans from like cavemen or from the Bible, how did they move like if they were like different, their muscles were different?
Okay. Interesting question. It is important to acknowledge that evolution takes millions of years. And in reality, we are not that far away from, we are not millions of years away from cavemen. Cavemen, their muscles also relied on sliding filament theory. If you look at bears, their muscles rely on sliding filament theory. If you look at foxes, dogs, cats, whatever, they all have sliding filaments. When I say evolution, I mean like 65 million years ago, when actually even longer than 65 million years ago. The Earth is estimated to be around like 4 billion years old or so. I mean, from the very point bacteria first appeared to the very first animal with muscles, and that can be like 2 billion years ago. In reality, that is very far away. The Bible and Jesus and cavemen, those are all still very close to us if we think about time in a real sense. Does that make sense, Daniel?
Yeah.
Yes. It is important to acknowledge that evolution will take millions of years, and we are not millions of years away from the Bible or cavemen, for example. If I just go online and I search up oldest copy of Bible, the oldest copy of the Bible was okay, it's not giving me a date. Okay. Okay, hold on. Give me a second. Okay, so it says the oldest codex of the Bible was written in about 1008. So 1008 to 2002 is, I mean, really, that's like 1,000 years. That's nothing compared to the Earth's geological time frame. If we're talking like 65 million years, well, then you have evolution. You have certain methods of maybe the myosin head gets more powerful or something. I don't know. But the Bible is not old enough to the point where I can say that, oh, they did not have myosin heads in the Bible. Definitely the Bible is not old enough. Is that okay, Daniel? Okay.
Oh yes. Yes.
Okay, great. Yeah. Yes, Derek, what's up?
Wait, isn't it 2022, not 2002?
Yes, it is 2000, it is 2022. I was saying that did I say 2002?
Yeah, you did.
Oh, my bad. Sorry. I wasn't even alive until 2002. But I mean, in reality though, like 2022 to 2002, 20 years in Earth's geological time frame is like a second to the Earth. 20 years is nothing. And we might live a quarter of our lives in 20 years, but to the Earth, it's gone in a second. It passes like in a blink for the Earth. Okay, any questions, anybody else? Okay, wow. Very interesting. That was cool. Honestly, I have not had such young children ever ask me such meaningful and important questions. It is interesting to have to tell you guys to think of ourselves as a speck within Earth's geological time frame. I mean, we are here for like, I don't know, a minute to the earth, and then we are gone, and then the next generation, and then the next generation. The earth has been here for so long, and we live for 70 years or so, and 70 years in 40 billion is nearly nothing for the earth. And so it is interesting to have to think of ourselves as this kind of speck in the time frame of the earth. What's up, Derek?
Wait, hasn't it only been like 4 billion, not 40 billion?
Yes, it's 4 billion. I did say 4 billion there. I definitely think I said 4 billion. And if I accidentally said 40 billion, it is 4 billion. Not 40 billion, 4 billion. Four, just the number 4, no zero. Okay. The meeting is going to end in 5 minutes, which means I will probably have to start a new meeting for us to play the Gim Kit. Is that okay with everybody?
Wait,
Yes.
wait, were you Gim Kits?
Yes, Gim Kit.
When do we start doing that? When did we start doing that?
Just last class, actually, someone really wanted to do a Gim Kit, so I said, okay, I'll make a Gim Kit, and then some people really liked it, so I said, okay, we'll keep on doing Gim Kits.
Yeah. Okay.
Okay, great. So those of you who want to play a Gim Kit, oh,
Hold on, which game mode will we do?
what's up?
Which game mode will we do?
I've never.
I don't know, whichever one you want, I suppose. Okay, but those of you who do want to play the Gim Kit, feel free to rejoin the meeting. I will set up a new one because we're at 4 minutes and we're running out of time, and I'm not paying multiple hundreds of dollars for extended time. But those of you who don't want to participate in the Gim Kit, that's completely fine. I will end the meeting, and I hope everyone has a good week. And then when I do see you back for Gim Kit, I hope you enjoy the Gim Kit. Okay, great. Thanks, guys.